Hi and welcome to this refresher on plate tectonics. My name's Pete Rowley. I'm Senior Lecturer in Geology at the University of West of England in Bristol. So plate tectonics is the process by which lithospheric plates move. The entire thing is driven by gravity, and lots of the geological processes and features that we know of are basically driven by this process. So earthquakes, the presence of mountain ranges, the presence of sedimentary basins, volcanic processes, erosion, the presence of our atmosphere, all of these are ultimately products of plate tectonics. So before we move on, just a quick bit of terminology to make sure we're all using the right words in the right ways. One of the most important ones is that plate tectonics is not the same thing as continental drift. Continental drift is a phrase that existed before the theory of plate tectonics was put forward to describe how, for example, if you look at a globe, it looks like you can close up both coastlines of the Atlantic Ocean and everything seems to fit together. So continental drift describes the observation that it looks like continents might have moved around in the past. Plate tectonics is the scientific theory which describes not just the fact that the continents are moving, but also the processes which cause that to happen. So really we shouldn't be using the phrase continental drift anymore. That belongs firmly back in the 1950s. It's very common when talking about plate tectonics to talk about the behavior of the crust, but actually it's much better to talk about the lithosphere. And the lithosphere describes the rigid parts of the Earth which make up the tectonic plates. And the difference between lithosphere and crust is that the lithosphere contains both the crust and part of the mantle which is also cold and rigid. And then if we're going to describe the mantle, one of the things to just bear in mind when we're talking about this is that although the mantle is ductile and can flow on geological timescales, it is not a liquid. Okay, the mantle is a solid material. So to describe and understand plate tectonic processes, we need to first of all understand what's going on within the Earth in terms of generating heat. And there's three main components to the heat within the Earth. The first is from the first accretion of the planet 4.5 billion years ago, all of those asteroids and planetoids and lumps of rock impacting together to form our planet let out a huge amount of heat, and there is still a good proportion of that heat from our formation remaining in the planet. We then have a couple of processes which are giving off more heat. The first is gravitational settling, so dense materials finding their way deeper into the planet, and as they transfer down, energy is given off. And then finally radioactive heating, and in particular the radioactive decay of uranium, thorium and potassium. And these are present in quite large quantities in the mantle, although fairly low concentrations, and they're present in much higher concentrations within the crust. The graph on the right there just shows you how much heat has been given off by these different radioactive processes through time, and the message to take home here is that actually there was a lot more heat being given off by radioactivity in the early Earth than there is at the moment. So if we're going to look at the structure of the Earth, hopefully everyone's familiar that we've got an inner core, an outer core, and then a mantle on the outside. And the mantle itself can be divided into kind of two layers. We have a broad lower mantle, and then we also have a slightly narrower upper mantle. Now, the important thing, I've already raised this, but just to make the point again, is that when we look at the state of matter in these different materials. The inner core is a solid iron nickel. The outer core is also iron, but the pressure conditions in the outer core are such that it's liquid, and it's the movement of this liquid that generates our magnetic field. The mantle on normal timescales would be thought of as a solid. If you were to dig down into the mantle, were that possible, and hit it with a hammer, it would ring like any other rock. Now, as we get up closer to the surface, it's worth noting that the different thicknesses of our very upper layers vary quite a lot. And this upper mantle is the kind of fluid, if you like, on which plate tectonics occurs. So we have this slightly confusing situation where the mantle on a short timescale, on a day-to-day timescale, is a solid, but on geological timescales of millions of years, it flows. A good comparison for this is something like pitch or tar, which is solid if you pick it up, but if you allow it to flow for decades or centuries, you'll find it behaves in quite a liquid way. There is some people use glass as an analogy, because when you look at old windows, medieval windows, sometimes they bulge in places, and people have argued that this is because glass isn't a full solid and it flows over time. That's actually a false comparison. The reason for the bulging in glass is because of the way glass used to be made, which was blown and then cut and rolled out. So they weren't able to create flat panels of glass in quite the same way we do it for modern windows. So the glass analogy isn't so good, but that's the kind of rigidity of material we're talking about in the mantle. So we have this ductile mantle, and on top of that we've got this lithosphere, and the lithosphere is made up of crust and cold mantle that's kind of cooled against that crust. So when we're talking about tectonic plates, it's not just crust, it's also this rigid layer of mantle that's been stuck on underneath. And if you look at mid-ocean ridges, then the lithosphere might only be a few, 6, 8, 10, 12 kilometers thick. Whereas if you look in normal oceanic basins, it's maybe 35 kilometers down to the base of the lithosphere. In normal continental settings, like here in the UK, it's probably about 80 kilometers down. And if you go to active mountain belts such as the Himalaya or the Andes, then you have to go down as far as 220 kilometers to get through the whole of the lithosphere. To put that in context, the deepest we have ever drilled is the Kola super deep borehole that the Russians took charge of in the 1980s, and they managed, I think, 12 kilometers. So we have barely scraped the surface of this planet. In terms of spatial distribution of different tectonic margins, this maps a nice summary of that. In red lines, we have divergent margins, or our mid-ocean ridges. In blue lines with the little tick marks on, we have our subduction and thrust zone type of tectonic margins. Scattered around there in the red dots, we also have volcanism. If you're interested in the volcanic processes, there's a separate booster talk available for those. So when we're talking about these different types of margin, hopefully you're all familiar with this kind of image. There's several different bits of terminology that are used. So spreading ridges or mid-ocean ridges tend to be referred to as divergent plate boundaries, and subduction zones we talk about as convergent plate boundaries. There's been some use in the past of whether boundaries are constructive or destructive. We try to avoid that terminology these days because actually it's not necessarily very obvious that, for example, a subduction zone is destroying material when actually it's also generating magmatism that's bringing new material up to the surface and causing crustal thickening. So the the terms constructive and destructive are not used so much these days. To understand what's driving plate tectonics, we have to think about what these different layers within the planet are doing. So we have our lithosphere on the top. Underneath that, we have mantle. Below that, we have the core, which is separated into outer and inner core. Now, we talked earlier about the different heat producing processes in the Earth. It's worth thinking about, of all the heat that escapes the planet, where it's coming from. And about 22% is originating from the core, about 32% from the lower mantle, 22% from the upper mantle, and about a quarter of the heat escaping the Earth is being generated within the crust. And part of this is because the crust is where the lighter elements tend to get concentrated, and what are called lithophile elements, which are elements that chemically like to bond to some of these lighter elements. And some of our most radioactive or common radioactive species like uranium and thorium and potassium tend to get concentrated in the crust because they like bonding chemically to those crust forming elements like silica. So we have this heat flow, and different layers within the planet are convecting. So convection is just the process of hot material at the base of a layer rising buoyantly upward, cooling at a surface, and then sinking back down again. And this convection drives a kind of cyclical motion. We have convection in at least two separate parts of the Earth. We have convection in the outer liquid core, and we also have convection in the mantle. And this convection in the mantle is related to plate tectonic motion. Now, if we're going to think about what's driving plate tectonics, perhaps the best place to start is the mid-ocean ridges, because this is where we can imagine our oceanic crust moving apart from each other. And one of the ways this has been visualized in the past is that these convection cells, this rising material from the mantle, might come up and then push these plates apart from each other. Now, the thinking on this has changed quite a lot over the last 15 or 20 years or so. And the general thought now is that actually that push apart from underneath is probably quite unlikely. Probably the bigger effect at the mid-ocean ridges is this relative height difference right at the ridge. If you look at this illustration, you can see the crust right at the ridge is higher up. It forms a mountain range relative to the crust further away from the ridge. And this height difference, although it looks insignificant in this illustration, you have to bear in mind represents perhaps 3 kilometers of altitude difference across a mountain range which is tens of thousands of kilometers long. So the mass of this mountain range is huge, and it wants to spread. So this mass at the mid-ocean ridge will force these oceanic plates apart. So there is this element of what we call ridge push. But that's not the main driver of plate tectonics. The driver for this is that as oceanic crust ages, as it moves away from the ridge, it cools down, it gets penetrated by more seawater, it gains more sediment. And so the crust itself cools down, and that means it's able to accumulate more cold mantle underneath it. So it cools a thicker layer of mantle underneath. So the lithosphere itself starts thickening quite substantially. This means that by the time it's got to a couple of 100 million years old, the oceanic lithosphere can be thicker, colder, and therefore denser. And importantly, it gets to a point where it's denser than the hot mantle underneath. At this point, subduction can initiate, and this cold oceanic slab will start sinking into the mantle. And this gravitational pulling of these cold surface slabs is thought to be the main driver for plate tectonics. One of the most interesting things about subduction zones is that as time's gone on, we've got quite good at understanding and visualizing the processes going on. And it's not always that straightforward. So subduction zones are quite large scale features, but we have ways of imaging them using our seismic monitoring network that's located around the world. And because subduction zones are related to some of the largest and most destructive earthquakes, they also happen to be places where we have very densely monitored seismic networks. So every time an earthquake goes off anywhere on the planet, those earthquake waves travel through the Earth and are then detected at all the different seismic stations around the planet. And this gives us a process which is identical to ultrasound used for imaging, for example, babies and medical conditions and all sorts of other things. But we're using lower frequency, longer wavelength signals because they're seismic waves, not ultrasound. But it's the same process. And we can use this to then image slices through the Earth. And what we find is that the subduction zones are incredibly easy to image because these subducting oceanic slabs, which are cold and dense, have different seismic wave velocities to the warm, slightly more fluid mantle. So these diagrams on the right hand side here are showing you different cross sections through parts of Northeast Asia where we have different parts of subducting slabs, and marked on in white circles are the locations of earthquakes along those zones. So you can see the earthquakes are tracing generally the upper boundary of these subduction zones. And plate tectonics is absolutely critical to another process, which I'll talk about in another booster, is this plate tectonic driving of magmatism and the formation of volcanic activity. I describe this diagram in more detail elsewhere, but it's important to remember that plate tectonics is intrinsically linked with volcanism. You can't have one without the other. So we can all recognize this as a modern day geographic map of our planet. What I'm going to do is just step you back through time to look at how plate tectonics has changed the distribution of these continents and our ocean basins over the last 200 million years. So if we step back 50 million years, what you'll notice is that the Atlantic starts to close, or rather it's earlier in its opening. And here we are now also being able to see the kind of processes which were required to assemble modern day Europe and Eurasia. So you can see here lots of island archipelagos making up what is now Central and Southern Europe. This is us in the very early stages of beginning to form the Alps. So we're going to step back now in increments until we get to our most recent supercontinent. So at this point we have Pangaea, but it's absolutely critical to remember that Pangaea is only the most recent supercontinent in Earth's history. So this is a very simple illustration that shows the different supercontinents which have been present through Earth history. Now, Earth formed about 4,500 million years ago, or 4.5 giga years ago. And what you'll notice here is the very earliest supercontinents, Valbara and Ur, formed something like 3 billion years ago. So there was at least a 1.5 billion year gap where we did not have any supercontinents, or perhaps even any continents at all. We then very rapidly start accumulating continental crust to form Kenorland, and then eventually Columbia and Nuna, and Rodinia, Pannotia, and then finally Pangaea. And between each of these supercontinents were periods of time where parts of this were broken up into much smaller units of landmass before they were then reassembled into supercontinents again. Now this presence of supercontinents is really important because it's giving us a clue to when actually we had subduction happening. We can only form continental crust by subduction processes because it's that subduction of oceanic lithosphere which generates melting, and the magmatic intrusion then of andesitic style rock is what produces the kind of continental crust that we have today. And the critical difference between oceanic crust and continental crust is that continental crust has this silica-rich andesitic granitic chemistry that means it's nowhere near dense enough to sink back into the mantle. So once you've formed continental crust, it has to stay floating around on the surface, whereas oceanic crust is able to recycle. As a result, the oldest continental crust we've got on the planet is about 3, maybe 3.5 billion years old. And the oldest oceanic crust we have on the planet is maybe 220 million years old. So there's an order of magnitude difference in the age of these two types of crust. The way this links into the plate tectonic story and the presence of these supercontinents is that if our supercontinents only started forming about 3 billion years ago, that indicates that before then, we probably didn't have continental crust. And actually, plate tectonics as a process probably was not occurring in the way we see it today. So this beginning of the supercontinent cycle is really where plate tectonics itself starts. So it's probably not true to say that plate tectonics has happened throughout Earth history, because it's very likely for the first 1.5 billion years of Earth history, plate tectonics was not occurring in the way that we recognize it today. When we're talking about supercontinents, it's worth bearing in mind that supercontinents are unstable. We know this intuitively because we know there's been several different supercontinents, but it's worth bearing in mind and thinking about why this is the case. And the driving force here is that when you have a continental collision, we form a large static mass of lithosphere on the surface of the planet. And any subduction that had been occurring to close those oceans, to seal it all together, has to stop. As a result, we're no longer feeding new oceanic or old cold oceanic crust underneath this region. And so the convection has to stagnate. The convection of the mantle underneath there will stagnate. The oceanic crust, which remains on the other side of the planet, if you like, in these large, almost planet-spanning oceans, will subduct at the edges of the continents. And the only way to accommodate any more movement within the mantle is for this melting material to find a way up under this supercontinent that we formed. So by stopping subduction underneath the supercontinent and triggering new subduction at the edges of the supercontinent, we force the formation of mantle plumes. And these hotspots rise up and end up punching through our supercontinent and triggering the development of new ocean basins. So our supercontinent comes together, it's there for perhaps tens or hundreds of millions of years, and then hotspots punch through, breaking it apart. And we can see this really nicely if we look at the breakup of Pangaea. So this is a map of Pangaea showing the modern continent outlines in black. And these red spots are where we had hot spots or mantle plumes upwell and trigger the formation of new ocean basins. And as you can see, there's 3 of them running up through the Atlantic. You have one just off the Congo, one just south of West Africa, and another one coming up in Iceland between Laurentia and Baltica. And it's the firing up of these mantle plumes that drives the opening of the Atlantic, and then we have another 2 punching up between the Congo and India and East Antarctica, which drive the opening of the Indian Ocean. And critically, the driving of that ocean is what pushes India incredibly rapidly up into the Asian subcontinent, and we end up with the building of the Himalaya. So just to give you a graphic representation of this, the mantle plume arrives at the base of the crust, it causes upwarping and then a gravitational collapse because we've got a high which has to want to fall apart. So we thin the crust, we start forming rift valleys, which eventually becomes a linear sea, which is what we're starting to see in the Red Sea now. And then we have eventually the development of a mature ocean. So we've split this continent apart to form an ocean basin. Eventually, this oceanic lithosphere will cool down enough that it will begin to subduct, at which point we can start consuming this ocean again and bringing these continents back together to form a new supercontinent. So, on that note, the idea to bear in mind is that Pangaea is only the most recent supercontinent of our cycle, and there will be more in the future. There's a list of resources here that I hope you might find useful, in particular Christopher Scottese's reconstructions, some of which I used in this presentation. If you've got any questions or would like more information, please do get in touch.